Hello friends, in today's class we'll talk about another finite state machine model called NFA, Non-Deterministic Finite Automata. Okay, so next part here is next model that we are discussing here is non-deterministic finite automata. Okay, so NFA stand for non-deterministic finite automata. So this is the model where the new term here is non-determinism. Non-determinism. Okay, so non-deterministic machine are like deterministic machine, but here the main difference here is this is the transition function. So Q sigma Q0 transition function set of finite state, everything is same. The only difference here is the transition function, and the definition of this transition function is Q cross sigma can be mapped to 2 to the power Q. Okay, and when we say 2 to the power Q, this is about all choices. Okay, so if we are having a state, suppose we are having Q as a set as Q0 and Q1, then 2 to the power Q is the power set of Q, and it represent nothing. It represent only Q0, it represent only Q1, and it represent Q0 and Q1 both. So the typical transition here will look like this. The data function will on Q0 on input, suppose alphabet is A, where it will be mapped. So the option is it can be mapped anywhere. If you don't want to, so phi or empty set is if we don't want to define the transition. Now here, if you say Q0 and Q1, these are the single choices. Okay, so these are the single choices. Now you can define the transition multiple times. So now you can have a situation where Q0 on input A is making a self loop and also going into another state. Let's say Q1, hypothetical example. So now this is possible. Okay, this is possible, and if we don't want to define phi, means that suppose Q0 is not defined over A but directly defined over B, and it is going to the state Q1. This is also allowed in case of NFA, non-deterministic finite automata. So more flexibility is given to this given to this NFA, and we'll see few more design, and we'll also comment that is this flexibility, or is this power of non-determinism changes anything in finite state machine. Okay, so let's see a few example of non-deterministic finite automata. Here we are talking about a non-deterministic finite automata, and in this non-deterministic finite automata we want to construct an NFA which accept all the string ends with AB, starts with AB, and the substring AB. Okay, so these are the three typical DFA we have already seen. Now to design the NFA, we have to more concern with the pattern part. That what is the pattern? So pattern says that the last two alphabet is A and B, but the first two alphabet here, the first part of this, I can write any string. Okay, so the definition of this part is pretty simple, that I can write here any string over A and B. Okay, so I can write anything over here. Starts with AB. What is the pattern over here? That the first two alphabet will be A followed by B, and the later part again it is anything. Okay, anything I can write. The first two NFA designs impose the restrictions on the position of AB, ending position and the starting position, but the substring part does not impose anything. So what is mandatory for the substring is that there should be an AB somewhere. If you want to end anything, it can end with anything over A and B, and if you want to start the string, then it can also starts with anything, any string. Okay, so that is the idea. And this pattern, if you have a good insight about this pattern, then your design of NFA will be pretty easy. Okay, let me translate few things over here. Anything, okay, so anything, any string of over A and B is defined as a single state. So let me just put this diagram here. Unlike our previous discussions of DFA, so I'm just directly putting a diagram. So this is my state, and in this state I can say it can be A or B, but when it comes to the ending part, there must be an alphabet A followed by alphabet B, then I can reach to the final state. Let me name them as Q1, Q2 and Q3. Now if I just put a table over here for this machine, then it will be Q1 on input A. Okay, so Q1 on input A, we are having a situation where Q1 on input A is going to the state Q1 as well as Q2. On input B, it is only Q1. Q2 is not defined on A, and on input B it is going to the state Q3. Q3 on input this, both are blank. Okay. Now that is the typical definition of non-deterministic finite automata. Here you can see here that there are two transition on input A. One remaining Q1 and another goes to Q2. And that is a multiple transition that we talked about, that for the definition of NFA. Few transitions are not defined, which is totally valid. So multiple transitions, single transition, and if you don't want to define, it is totally fine with non-deterministic machine. Starts with AB. So now this is the machine that starts with AB. So now we have a Q1 state, and here on input A it will go to this let's say Q2, and on input B it will go to Q3. It's a final state, and anything comes and that will be accepted. So this your ends it starts with AB, and substring AB will look like this, that it will be there is state Q1 which is accept any string over A and B, and then there will be A, and there will be Q2, and then there will be B, and then there will be Q3 final state. Okay, now just label them that this machine is ends with AB. This one, this machine starts with AB, and this one is a substring AB. So that is your NFA, and I don't want to go to the proof part, but here the NFA model is DFA model. Whatever DFA can do, similar model that NFA can also do. Okay, so that is your NFA, non-deterministic finite automata.